Thank you. Good afternoon, everybody. Can you hear me? Okay. So during the past 25 years, my research at the University of Chile has dealt with many topics in geostatistics, including spatial prediction, change of support, design of random field models, simulation algorithm, and also with applications in mineral resource assessment, geological uncertainty, geotechnics, and geometallurgy. But today I want to invite you to a journey into covariance models for spatial data, which corresponds to one of my recent research. It has provided some theoretical and practical developments. So fasten your seatbelt, secure your table. The journey will begin. Okay? Okay, the goal of the presentation will be threefold. On the one hand, I want to review some characterizations of covariance functions that are defined in the d-dimensional Euclidean space, or on the d-dimensional sphere, or on the product of such spaces. And the primary motivation for choosing these spaces is to model not only data located in the classical Euclidean space, but also data distributed on the surface of the Earth, as well as space-time data. On the second hand, I want to present some parametric families of covariance functions that provide flexible models in terms of shape, short range, and large range structure. And finally, I also want to suggest some novel applications of such models in the geosciences. The scope of the work is for real-valued stationary or isotropic random fields, which can be scalar or vector random fields. Here is the outline. I will begin with some brief review of mathematical background. This is my favorite part. Then I will focus on stationary models in the Euclidean space, then in the product of two Euclidean spaces, then on the sphere, and the product of the sphere and Euclidean space. And I will finalize with some discussion conclusions and references. So first, a little mathematical background. Okay. I hope that everyone is familiarized with spatial functions. I will use some of them, or most of them, in this presentation. I can forgive you if you are not so familiar. The main functions will be the Gegenbauer polynomials. They are also called the ultraspherical polynomials, and they play a central role in the harmonic analysis of random fields on spheres. I will also use some Bessel functions, J and K, and some hypergeometric functions. They are a rich class of functions that generalize most of the well-known ordinary functions. I will also speak about symmetric or Hermitian matrices that are positive semi-definite or conditionally negative semi-definite. Then these are matrices that fulfill the conditions written here for positive semi-definiteness or here for conditional negative semi-definiteness. Okay, matrices will be denoted with a bold, and they will be of order P. It means that I will focus on P variables. I want to focus on multivariate setting, and most often the matrix will be real, but sometimes it will be also complex, because some spectral characterizations need the use of complex matrices. And then I can define some order relation between symmetric or Hermitian matrices of order P. So it is a loner order. A matrix A is said to be greater than matrix B if the difference A minus B is positive semi-definite. And this order relation makes it possible to extend the common properties of scalar functions to matrix-valued functions. So one can define matrix-valued functions that are non-negative, non-increasing, convex, multiply monotone, or completely monotone. Multiple monotonicity is a concept that was introduced by Williamson in 1956 for scalar functions. And it refers to the fact that the successive derivatives alternate in sign up to some given order. And for infinitely differentiable functions whose derivative alternate in sign at any orders, we speak of completely monotone functions. The derivative or any operation in the presentation should be understood as element-wise. So we make the derivation or the differentiation for each element of the matrix-valued function. Okay, now that you are familiar with mathematical background, let's turn to the first class of matrix-valued covariance functions, which are those defined in a d-dimensional Euclidean space. A matrix-valued covariance function is a set of direct covariances, which are the diagonal entries, and cross-covariances, which are the off-diagonal entries. And the goal here is to present some characteristics of these covariances and some examples that go beyond the linear model of coregionalization, which is probably the most used by practitioners when dealing with multivariate data. But the fitting of such a linear model of coregionalization may be painful when we are in a highly multivariate setting, when the shapes of the direct or the cross covariances are different, or when the correlation ranges are different. So let's begin with some characterization of stationary covariance functions. The second-order stationarity of a random field means that its covariance function exists and only depends on the separation vector between the paired locations. And the most general characteristic is to be positive semi-definite. That is, when one constructs a matrix with all the direct and cross covariances among a set of n locations, x1 to xn, one obtains a symmetric positive semi-definite matrix. And there is a one-to-one correspondence between covariance function and positive semi-definite functions, which is a well-known result by Kolmogorov. In principle, we should write the covariance function as a function of the two locations, but here I will write it in the stationary context as a function of the lag between the two locations. Among the properties of covariance functions, let's recall that if one takes the sum or the element-wise product or a mixture of covariance functions weighted by positive semi-definite matrices, or a limit of a sequence of covariance functions, one still obtains a covariance function. Also, if a stationary covariance function is continuous at the origin, it is continuous everywhere. And the restriction of a covariance function to a subspace still provides a covariance function, but the reverse may not be true. Now, if one restricts to continuous covariance functions, it is well known that they have a Fourier representation, and they can be written as a mixture of a complex exponential, depending on a frequency vector, omega, weighted by a Hermitian positive semi-definite matrix, f of d omega. And the matrix-valued measure f is called the spectral measure. It is bounded. It means that the integral of f over all the omegas is finite. And it is Loner non-decreasing. That is, every elementary matrix f of d omega is positive semi-definite. So this result is due to Bochner, I think in the 30s for the univariate setting, and to Kramer in the multivariate setting. Now, if one adds the restriction that the covariance is square integrable, then the spectral measure has a density, which is a lowercase f, and we can derive this spectral density by inverse Fourier transformation. So the density applied to any frequency vector omega provides a positive semi-definite matrix. Okay, one can also focus on isotropic covariance functions, which depend only on the norm of the separation vector. So I can identify the covariance with a function of a non-negative variable, which is a radial part or the isotropic part of the covariance. And it gives as an output a matrix of order P. So this radial function is indexed with the dimension of the original space in which the covariance was defined. And interestingly, in a multidimensional space, the only discontinuity that can have an isotropic covariance is at the origin, that is the nugget effect, sorry. Okay, if an isotropic covariance is continuous, that it can be written as a scale mixture of Bessel J covariances, which are this expression. These are a class of oscillating covariance functions. It means that except for the nugget effect, any isotropic covariance function in the Euclidean space is a mixture of such Bessel covariance and is fully characterized by the measure G, which is actually closely related to the spectral measure. Okay, earlier I said that the covariance may not be extendable to a higher dimensional space. There are some interesting exceptions. For instance, Rudin shows that continuous stationary isotropic covariance in a ball can be extended to the whole space. And another result was given by Porcu and others last year, which gives a one-to-one correspondence between matrix-valued and scalar-valued isotropic covariances. Okay, last part of characterization for Euclidean space. It is a spectral representation for the radial part of an isotropic covariance, which is also square integrable. So we had the Fourier transform for the covariance. In terms of the radial part, we have the spectral density, which is also a radial function. And the relation between the radial part of the covariance and the radial part of the spectral density is given by a Hankel transformation, which is this integral transformation that involves a Bessel function. So all these results are useful to construct new models, also to design a simulation algorithm. I will turn to some examples of parametric families of covariance functions in the d-dimensional Euclidean space. The first one is the isotropic Gaussian covariance, which is a basic building block for many covariance models. So the radial part of the covariance in RD is, it depends on two parameters, matrix-valued parameter beta, which is a scale parameter, and the matrix sigma, which is a variance-covariance matrix. It is a covariance function at the origin. I recall that the notation here is for matrix is element-wise. So the entry ij of the matrix-valued covariance is obtained by taking the entry ij of the matrix sigma and the entry ij of the matrix beta. So one question is, under which conditions on the matrix-valued parameters do we obtain a valid covariance model? And the set of sufficient conditions is given here. So element-wise inverse of beta should be positive, so should be conditionally negative semi-definite. And sigma multiplied element-wise by beta raised to power minus half d should be positive semi-definite. So this condition guarantees that the spectral density matrix is positive semi-definite for any frequency, therefore that the model is valid. A second example is a well-known model for spatial statisticians. It is a Matheron covariance. The definition involves a modified Bessel function k of the second kind. And this covariance, well, it is standardized to a unit variance. It is a correlation function. It depends on two positive parameters, which are alpha, a scale parameter inversely proportional to the correlation range, and nu, which is a smoothness parameter. So if nu tends to 0, we get a pure nugget effect. If nu is 0.5, which is the red one, we get an exponential covariance. If nu tends to infinity, we tend to a Gaussian covariance up to some rescaling. So this Matheron covariance is valid in any d-dimensional Euclidean space. And it has been, it is a gold standard for applications in environmental and atmospheric sciences. So in the multivariate setting, one can define a matrix-valued version of the Matheron covariance by replacing the scalar parameter by symmetric matrices of order P. So this construction is due to Gneiting and others in 2010. And the model depends here on three matrix-valued parameters: alpha, which is a scale parameter, nu, which is a smoothness parameter, and I also introduced sigma, which is a variance-covariance matrix. The question now is to determine the conditions on these parameters in order to ensure that the model is valid in the d-dimensional Euclidean space. And this question was addressed by Gneiting and others, and also by Apanasovic and others in 2010 and 2012. And they have found some conditions that are necessary and sufficient in the bivariate setting, but only sufficient in the multivariate setting. And these conditions in practice are often quite restrictive, and they lead to different variables that have very low cross correlations. So one of my recent research work was to find out more flexible conditions. And I explored two manners of proving that a function is a covariance, that is a positive semi-definite function. The first one is to write the function as a scale mixture of known covariances. In this case, the Matheron covariance is an inverse gamma mixture of Gaussian covariances. And it is also a gamma mixture of Wendland covariances, which are a family of compactly supported covariances. And the second manner to prove positive semi-definiteness is to set the parameters in order to ensure that the spectral density matrix is positive semi-definite for any frequency. So all in all, I obtained several sets of sufficient validity conditions. They have been found in two recent papers, one of last year and another one of this year. And I will just put here one of these conditions in theorem 2. It involves a matrix value hyperparameter, psi, together with the other parameters, alpha, nu, and sigma. And recall in all these expressions, operations are element-wise. So to get some simpler condition, let's particularize with several choices of the hyperparameter psi. So I made some choices of psi here. I obtained some simpler sets of conditions on the main parameters, alpha, nu, and sigma. So do these conditions improve the ones that were previously established by Gneiting or by Apanasovic? So I made a test with a simple example. It was considering p-random fields in the 2D plane with this parameterization for alpha, for nu, and for sigma. I set all the parameters equal in the diagonal elements, and all are equal in the off-diagonal elements, but with a different value as the diagonal ones. And the only free parameter here is a rho, which is a collocated correlation coefficient between the variables. So what is the maximum value of rho that I can obtain with the conditions of Apanasovic, which was a standard of 2012? I found that rho could not be greater than 0.064. Now, when I use one of the conditions of the previous slide, I find that actually rho can grow until 0.52. It means 8 times higher. So I hope that this example will motivate the use of the multivariate Matheron model, because it shows that it is possible to impose some different scale parameters or some different smoothness parameters to the direct and cross covariances without sacrificing too much the correlated correlation coefficient. Okay, I left the best model for the last example. I called it the Gauss hypergeometric covariance. So in the univariate setting, the formulation of the covariance involves a hypergeometric function. This is 2f1, the Gauss hypergeometric function, and also 4 parameters, the range A, and 3 shape parameters, alpha, beta, and gamma. So in another paper I published last year, I showed some sufficient conditions for these parameters in order to obtain a valid covariance in the d-dimensional Euclidean space. And these conditions make the spectral density matrix be positive semi-definite for any frequency. The calculations were quite tedious because the spectral density of this model is expressed as another hypergeometric function, which is 1f2. Okay, but two properties of this model make it interesting, in my opinion. The first one is it is compactly supported. So if the lag R is greater than the range A, we obtain 0. So the covariance vanish after the range A. And the second interesting property is that this hypergeometric model generalizes practically all the commonly used models for geostatisticians. So if you make some particular setting of the parameters alpha, beta, gamma, you can find the spherical model and all the related models like the circular, the triangular, pentaspherical. You can find the cubic model, which is an upgrade of the spherical model. The upgrade is also called the Monte in the geostatistical literature. You can recover the ASCII model, which is a truncated power covariance. You can recover the Venn-Land covariance, truncated polynomial covariance, and asymptotically, if you set the range tending to infinity and the shape parameter also tending to infinity in some manner, you can find out the Matheron correlation and the Gaussian correlation. So almost all the models are contained in this family. I try to figure out what is the validity space for the parameters of this model. So here you have a 3D representation with parameter alpha on the vertical axis, parameters beta, gamma in the horizontal axis. So the smaller alpha, the less regular near the origin is the covariance. As for beta and gamma, they play symmetrical roles, so you can switch beta and gamma and you obtain the same model. And these parameters have an impact on the curvature of the covariance function. And the boundary of the parameter space is a surface. I try to represent it with some colored line for specific values of alpha. And all the classical models are located on this boundary. You have the spherical here, the ASCII, cubic, the Gaussian is on the top over there, the Matheron is here. So all the known models can be represented in this parameter space. Okay, this was a univariate model, so I try to extend it to the multivariate setting by considering matrix-valued parameters, the range A, the shape parameter alpha, beta, gamma. They are matrix now in bold. And I also added a variance-covariance matrix sigma. And if we focus on the spectral density, we can derive some sufficient validity conditions for the spectral matrix to be positive semi-definite. I hope that you will forgive me for this couple of conditions. There are more in the paper of 2022. The first set of conditions implies that the range A is the same for all the direct and cross covariances, and the parameter alpha that controls the short scale behavior is also the same. But in the second set of conditions, the entries of alpha are the same, but not the entry of A. It means that the direct and cross covariances can have different correlation ranges. Okay, let's go now through covariance models defined in a product of two Euclidean spaces. The motivation here is the modeling of space-time data and the generalization. I want to try to generalize a well-known model in space-time geostatistics, which is a igniting model. And in particular, my interest is to define covariances that are not space-time separable. That is, the covariance cannot be written as a product of a spatial covariance and a temporal covariance. And the non-separability, special statistician likes this. It allows to capture some complex relationships between the space and the time variations of a random field. So first, let's make some review of characteristic properties of stationary space-time covariances. The most general one is a positive semi-definiteness. That is, all the covariance matrices that I can construct from the covariance function must be positive semi-definite. from a stationary space-time covariance, you can define a purely spatial covariance, a purely temporal covariance. If you set the temporal lag to 0 or the spatial lag to 0, respectively. You can also distinguish if the covariance is separable as a product of a spatial and a temporal term, or it is non-separable. It can be positively non-separable for some specific space-time lag or negatively non-separable. If the covariance is furthermore continuous, we have a spectral measure F that is bounded, Hermitian, and non-decreasing. It depends F on spatial frequency omega and the time frequency omega prime. And if the covariance is also integrable, then it has a spectral density that can be obtained by inverse Fourier transformation. An interesting related result is a partial Fourier transformation. So if you take the covariance C and you make an inverse Fourier transformation, but only in relation to the spatial lag h, then you get a function of the temporal lag u, which turns out to be a covariance function for almost any spatial frequency omega. So if you take u equal to 0, you obtain the inverse Fourier transform of the spatial component of the space-time covariance C, which is a positive semi-definite matrix. But this result here is more general because it says that this is a positive semi-definite function of u. And it is useful for at least two purposes. One is to construct some explicit covariance models. I will show you some examples next. And the other one is to simulate random fields having such covariance models by means of spectral methods. I will show you also an illustration next. Okay, following with characterization, if instead of isotropy in the d+1 Euclidean space, which does not make sense with space-time data, we can define the component-wise isotropy. That is, the covariance only depends on the norm of the spatial lag and of the temporal lag, h and u. So this defines what I call here a multiradial part of a covariance. And the covariance is said to be spatially isotropic and temporally symmetric. And if we add the assumption that the covariance is continuous, that it has a representation as a mixture of a spatial Bessel covariance, omega d, and a temporal Bessel covariance, omega 1, and the mixture matrix G is related to the spectral measure of the covariance. So we have a lot of characterizations. Let's show with these theoretical results, we can construct different families of space-time covariance. The gold standard today is probably the Gniting model. It has been designed 20 years ago by Gniting. And it depends on two functions. There is a temporal function gamma. So it's a function applied to the temporal lag u, which must be an intrinsically stationary variogram. And there is a spatial function phi, which must be a completely monotone function. That is a function whose successive derivatives alternate in sign. And such a function can be written as a scale mixture of exponential functions due to a theorem by Bernstein. So if we particularize, we can get Gniting Gaussian covariance if I take the function phi as a pure exponential function. And this is, the name of the model is because the spatial component is a Gaussian covariance, which is obtained by taking the temporal lag u equal to 0. But for non-zero u, we still obtain a Gaussian covariance, but with a scale parameter and the variance parameter that depends on u. And the second well-known example is the Gniting Matheron covariance, where this time the spatial component is a Matheron covariance for a non-zero lag u. The scale parameter and the variance depend on u, but the shape parameter nu is a constant. So this was for a univariate setting, the Gniting model. So what about this model in a multivariate setting with two co-authors led by my colleague Denis Allard? I established a generalization of this model to the multivariate setting by considering matrix-valued parameters. So the shape parameters nu is a constant matrix, but the scale parameter and the variance-covariance matrix depend on three matrix arguments, A, B, and tau. Two constants, alpha, where is alpha? Here, and beta, and also a matrix-valued function, eta, here. And you find here some sufficient validity conditions to provide a model in the R-dimensional space cross R. So you need to check for the positive semi-definiteness of some matrices depending on nu and tau, the conditional negative semi-definiteness of other matrices depending on nu, A, B, and we also need the matrix-valued function eta to be a pseudo-variogram. That is, the entries of eta should be the variance of the cross increments for a given random field defined on the time axis. So if you want more details or more validity conditions, you can read this paper. And you will also find in this paper some algorithm, a spectral algorithm constructed purposely with this model. So to simulate a multivariate random fields in space-time with a igniting covariance. You see an example here for a bivariate random field. The first component is smooth because I set the smoothness parameter nu to 1.5. The second component is raw because the parameter is 0.5. And with a spectral algorithm, you can efficiently simulate the random field on very large grids with grid nodes that can be regularly spaced or not. Okay, another of my colleagues, Emilio Porcu, and we have also looked at generalizations of the igniting model. The first generalization relates to the fact that the spatial function phi is now a matrix-valued function. It is written with bold. And the temporal function gamma, we replace it by a matrix-valued function eta, which depends on both the spatial and the temporal lags. So we see again some validity conditions to ensure the positive semi-definiteness of the covariance. And we see that eta should also here be a pseudo-variogram, now for a spatially isotropic and temporally symmetric random field. And looking for even more general models, we replace the completely monotone function phi by a matrix-valued covariance, Fd, the rest of the model having the same structure as the igniting model. We use a temporal function psi here, and the matrix-valued parameter rho. So the motivation was to construct some non-separable space-time models that can be compactly supported. So if you choose the covariance F with a compact support, you will obtain, it is a spatial covariance here, you will obtain a spatio-temporal covariance with a compact support in space. With the igniting model, you cannot do this. The igniting model, you have a completely monotone function that decays asymptotically to 0. So for sufficient validity conditions, that was pretty difficult to establish. We found that the covariance Fd must be a valid covariance, but not in Rd. It should be a covariance in a space that is augmented by 2k dimensions, with k being an integer greater than 1. And the function psi should be, or should have entries that are the primitive of a multiply monotone function, or it can be a mixture here of a square function on some trigonometric functions weighted by positive semi-definite matrices, or it can be a combination of the two previous cases. So the proof is quite complicated. It involves use of the partial Fourier transform. There is a Monte operator. There is also some isometric embedding of a metric space into a Euclidean space, with references to early works of Schoenberg and Matheron. Okay, let's now change to something a little new, which is models defined on a sphere, a d-dimensional sphere, SD. The main application deal with a two-dimensional sphere, which represent the sky in the case of astronomical data, or the Earth in the case of geophysical, environmental, or climate data. So on the sphere, the notion of stationarity, which is invariance under space translation, has to be changed to that of isotropy, which is invariance under rotation. So one defines an isotropic covariance as a covariance function that only depends on the geodesic distance on the sphere, which is also known as the great circle distance, or the shortest path distance on the sphere, which is the function theta, the geodesic distance. It is valued between 0 and pi when one considers a sphere that is with a unit radius. So sometimes one speaks of a geodesically isotropic covariance function. So under an assumption of continuity, these isotropic covariances have a spectral representation that involve an expansion into Gegenbauer polynomials. This is also called the ultraspherical transformation. The result here is due to Schoenberg in the univariate setting and to Yaglom in the multivariate setting. The weights B here in this expansion, they are positive semi-definite matrices. They are called the Schoenberg matrices, and they can be recovered by the inverse ultraspherical transformation, which is this expression. From the covariance, you can obtain the Schoenberg matrices. So this is the equivalent of the Fourier representation in Euclidean space. Here it is an ultraspherical representation on the sphere. So some example. When I was looking for explicit models on the sphere, I had a couple of surprises because first, most of the models were only defined in the univariate setting. And almost all of them, or probably maybe all of them, were not compactly supported. That is, the correlation range was greater than pi, which is pi is the maximum distance on the unit sphere. So one of the most famous models is a multi-quadric covariance. I believe it was defined by Igniting 10 years ago. It depends on a scale parameter A and on a shape parameter nu, and also a variance parameter rho. So if we extend this model to the multivariate setting, we replace the scalar parameters by matrices. And when we work with the spectral representation, we can show that the Schoenberg matrices are positive semi-definite, that is, the model is valid in the sphere, if the following conditions are met. So the three parameters, A, nu, and rho, should be positive semi-definite up to some shift for the new matrix. The second model is the exponential covariance. This is just like a multivariate exponential covariance in the Euclidean space, except that you replace the Euclidean distance h by the geodesic distance theta. And again, if you examine the Schoenberg matrices and with some tedious algebraic manipulation, you can find some sufficient conditions on the scale parameter nu or on the variance covariance matrix rho for the model to be valid on the sphere. So note that the conditions do not depend on the dimension of the sphere. So the model, the exponential model, is valid on a sphere of any dimension. And it is one of the very few models that has an expression depending directly on the distance, the geodesic distance theta, not on the cosine of theta. As a third example, I just mentioned here hypergeometric covariance with a lot of parameters, matrices A, B, C, and rho. So you see, it is a highly flexible model, but very intensive in parameters. So if you are interested in models of covariances on the sphere, I invite you to read another of my papers of last year. It was quite a productive year last year. The title says 22 covariance models on the sphere, and something like this. I had some dreams of equations, and then I write down and I obtain all these models. Okay, a particular case of all the previous covariances is that they do not vanish when the distance is less than pi, so they are not compactly supported. They have a low rate of decay. So I get interested in finding models with finite ranges together with their spectral representations in terms of Schoenberg matrices. And I found a wonderful result. I was quite proud of it. It generalized known results established earlier by other authors. So what does it say? If you consider an isotropic covariance with a range less than pi in an Euclidean space with an odd dimension d, just odd dimension, and you replace the Euclidean distance h by the geodesic distance theta, you automatically obtain a valid model on the sphere of the same dimension, d. It is valid for univariate and multivariate covariances. And the proof is really beautiful. It involves the multiply monotone functions that were defined by Williamson. It involves some connection formula between Gegenbauer and Chebyshev polynomials that were established by Richard Lasky in 1965. And it also involves a Monte operator defined by Georges Matheron in 1965 too. And one byproduct of this theorem is that you can also determine the spectral representation of the covariance on the sphere, that is the Schoenberg matrices, from the spectral representation of the covariance in the Euclidean space, that is from the spectral density. So for instance, if you can consider the Gauss hypergeometric covariance that I talked previously, and you can obtain the same model, so valid on the sphere. And because you can derive the spectral representation of the covariance, it is possible to simulate random field with such a covariance by means of spectral methods. It is based on the use of spherical harmonics or the use of Gegenbauer polynomials. And here you have an illustration with 3 random fields having a spherical covariance on the top, or a cubic covariance in the bottom, with 3 ranges, 0.5, 1.5, or 3. They are all less than pi, so the result is working. And the benefit of spectral simulation is the possibility to simulate on large grids, that is with a very fine discretization of the sphere at a very affordable computational cost. The last part of the presentation will deal with covariances on the product of a sphere and a Euclidean space. I can define stationary covariance as a covariance that depends on the geodesic distance on the sphere, theta, and the Euclidean distance on the sphere, on the space, sorry. And if you assume continuity of the covariance, you combine the previous characterization, you can obtain a spectral representation like this. It involves a Fourier ultraspherical transform with a measure f depending on an integer n and a frequency omega. The relative result is obtained by partial spectral representation. You can take the inverse Fourier transform of the covariance, and you will obtain some function of the geodesic distance theta, which should be a covariance function. Or you can take the inverse ultraspherical transform, and you will obtain something depending on the spatial lag h, which also should be a covariance function. So from this partial spectral representation, you can define explicit parametric families of covariance. The first one here is quite simple. It is a separable covariance. The second example is a Cauchy model. You have the marginal covariances on the sphere and in the Euclidean space being Cauchy type. Or you have here a model which is analog of the Gniting model. It was defined in space-time. Here it is on sphere time, which involves a function phi. And the gamma function here is a linear function of the geodesic distance. So we can construct these models. We can have the spectral representation. We can also define spectral simulation algorithm. You see here an illustration in the univariate setting for the covariance that is varying smoothly in time, but not on the sphere. So many applications on covariances refer to the modeling of space-time data, in particular data distributed on the surface of planet Earth and evolving in time, typically climate, atmospheric, or environmental data. Now, instead of the Earth, the sphere can also be a human head, with applications that relate to electroencephalography. You get different signals evolving in time associated with different locations on the head. As for the geosciences, which should be more of interest to you, I found several applications related to the modeling of direction-dependent variables. It happens with gradient variables, permeability, or with geotechnical variables. So let's show an example. It deals with the modeling of the rock quality designation, RQD, in a mineral deposit. RQD is a variable that measures the quality of the rock mass as a proportion of the core sample that is formed by pieces of more than 10 centimeters. So it is between 0 and 100. 0, all the pieces are less than 10 centimeters. 100, all the pieces are more than 10 centimeters. But this variable is a one-dimensional measurement. It depends on the direction of the core axis with respect to the direction of the discontinuities in the rock mass. So if you take a core at the same position but with a different direction, you will obtain a different value of RQD. So it is a direction-dependent variable, and it seriously complicates the modeling and the spatial prediction. So what was one idea? One idea was to see RQD regionalized not in 3D but in 5D. We have the product of the 3D space with a sphere which represents the direction of the core sample. So each data has 5 coordinates: the easting, northing, elevation, azimuth, and depth. And we can make all the geostatistics, modeling, anamorphosis, simulation, prediction, whatever, in the 5D space instead of the traditional 3D space. And you can obtain results like this. You can see spatial interpolation of RQD in a plane with a fixed elevation. But instead of a single map here, I can show as many maps as I have directions of interest. So I show the RQDs that should be measured along the north or along the east or along the vertical direction here. The black solid line is a confidence region, which is a region where the Kriging error is less than 90% of the variance. And the dots represent the data that are closeness in space, but also closeness in direction. So I hope that this will foster the interest in geotechnics or in other applications related to direction-dependent variables. Okay, I did not make any technical proof. You can find many results in books by Russian authors. I like them. Very thick textbooks full of equations. Okay, if you need more, you have some very interesting papers by Schoenberg. And if everything else fails, you also have the masterpiece of Georges Matheron of 1965. If you look at the table of content, you can find that he already tackled the hypergeometric covariance functions. So as a conclusion, I would like to stress the main motivation for the work. It's a need for models that are flexible to capture the complexity for space or space-time data, and at the same time depend on few parameters, so that can be inferred in a meaningful way. There is still room for more complex models, more complex spaces, for non-stationary models. And as a last word, all these models also are on demand in other fields, like in machine learning. There is a high interest in positive semi-definite kernels in machine learning. So here is a list of references. I want to acknowledge my agency, my department, center, IAMG also for inviting me, my co-author, collaborators all over the world. And I want also to make a dedication to Georges Matheron, whose work has inspired mine. This was a sketch given to me by my students at University of Chile. Thank you for your attention.
You haven't finished yet?
Yes.
We've got about 8 minutes for discussion. Okay.
Turn on your microphone. Thank you for a very instructive talk, quite mathematically oriented. I liked it. I have a question about the covariances that have holes, hole covariances in space or in time.
That are what?
Hole covariances with negative correlations.
With Hall effect.
The Hall effect. I know there are limitations on the hole itself. For isotropic in 3D, for instance, they have to be the negative parts have to be less negative than -1 over dimension of the Euclidean space. Things like that. I know you know that. The question is, we have also in time periodic effects. So, for instance, I have flow rates with the 2 monsoons. So I have this periodicity. There are holes, but they are not the same because there are 2 periods. So can you tell us whether this type of either space or time hole functions, hole covariances, how they fit into your characterizations and also the limitations, the properties that have to be honored?
Yes, I have found models with Hall effect in space, space-time, sphere-time also. I did not put them because it was pretty much material. But they are the same characterization. You can work with a spectral density, make some modification of a known model to get a Hall effect, for instance. It can be also directional Hall effect. So you have a Hall effect in vertical direction, but not in horizontal for space. For the sphere, for instance, I get a model with Hall effect by the turning bounds operator. So it's like the Monte. It's another operator that you can construct a covariance in a space with 1 dimension from a covariance in an augmented dimension. So with a turning bounds operator, with a no Hall effect model, you can obtain a Hall effect model.
Thank you.
So thank you for very many correlation functions. Now that you have shown me, I'll remember all of them, sure. So it brings me to the question, how should I determine these parameters?
Okay.
And how much data do I need to be able to distinguish between all of these parameters?
This is a question, for spatial statisticians. You know, for me, a geostatistician, maybe I will make the fit with least square. But I know for spatial statisticians, it's not a good thing. So they make some, they take a parametric family, maybe they make some simplifications of the parametrization in order to depend on a few parameters. And they can infer them by maximum likelihood or some simplified version of maximum likelihood. So I know the number of parameters in spatial statistics is, they want to minimize the number of parameters, but taking a trade-off to maximize the versatility of the model. So when you take a LMC, linear model of correlation, you have a lot of correlation matrices, and the number of parameters is too many. So with multivariate Matheron, you get more or less the same versatility, but with much fewer parameters. Maybe there are still a lot, but okay, it depends on the number of variables, the matrices. And the number of data also has an impact on how you parameters. My colleague Allard, for instance, you see the multivariate igniting model. It was an expression like this. But in the application, he made some simplification of the parameterization, and then you get a model like this with a few parameters.
Thank you.
Quick question. What's the difference between a spatial statistician and a geostatistician for you?
Spatial statistician, my experience, they are fond of modeling correlation structure, covariance with maximum likelihood. Geostatistician, we just calculate an experimental variogram and we fit a curve, you know.
Okay. Thanks.
It should be the same, but there are some conflicts between people sometimes, so you should be cautious when you do this.
Thanks for the advice.
Any more questions? Last chance.
I tried to understand your theorem about making planary variograms on this, putting them on the sphere. And I was not quite sure about whether I understood that and what the odd dimension must be.
Okay.
So when I have a plan, did you say that when I have a variogram in this on the plane that I can extend it to the Earth?
Yes. You take a. Let's speak about covariance instead of variogram. Okay. You take a covariance with range less than pi. It should vanish after pi in the Euclidean space. And you replace the h. It should be isotropic also. So you replace the Euclidean distance by the geodesic distance, and you obtain a covariance on the sphere with the same dimension as the space of the Euclidean space, but only if the dimension is odd. I'm not sure if it is even, because the proof works for the odd dimensions.
Excuse me, if I may, I got confused with this because the Euclidean plane is 2D and the sphere.
Yeah, you take a circular covariance in the plane, for instance.
So, and the dimension is not odd, so I don't understand it.
Sorry. It should be not on the plane, it should be on the 3D sphere, the 3D space. So you take a spherical covariance in R3, and you obtain a spherical covariance in the 3-dimensional sphere. Then you can restrict to the 2-dimensional sphere if you want. But you need to go from RD with an odd D to SD with the same odd D.
Okay, and then to take more or less the great sphere on that 4-dimensional sphere. So no.
4-dimensional.
I'm trying. So is that when I have a 3-dimensional sphere, is that the classical sphere because it's in 3 dimensions?
No,
it has a 3-dimensional
The classical
surface.
sphere is 2D. It's a flat surface. It's a 2D sphere in a 3D space, but it is 2D, the sphere.
Okay, so the Earth would be a 3D sphere.
Yeah, you need to work with S3, the 3D sphere, and then you restrict to the 2D sphere, if you want.
You can see it. S3, you cannot see it.
Yeah. I had in
But the fact is that
in Toronto, I had a video representation of the
with the odd
that sphere.
with the odd dimension, the proof you have some expansion which has a finite number of terms, and you can make some recursivity reasoning, and it works. And when you are in even dimension, it is an infinite series, and it does not work. It's like when you make the montée in one more dimension, it's very difficult, and with 2 dimensions, it's much easier. The same kind of problem.
Thanks. I'm going to present you now with the plaque
Okay.
for your
Thank you.
and your certificate. And you need a photograph.